this is the faster pwning assured talk, hardware hacks and cracks with FPGAs. We did our best to try to integrate FPGA into the title of the talk. My name is Dan Moniz. This is David Hulton.
Hey.
We're talking mostly about a series of collected, essentially FPGA projects that each of us has been working on. And for the rest of the talk, what you'll sort of see the trend being is that although I'm wearing the jacket, David represents the high end of FPGA hacking, and I represent the ghetto end of FPGA hacking. This monstrous green beast of a machine over here, which David will talk more in detail about, is David's. This teeny little green beast is mine. So we'll talk more about it in detail in a little bit, but that's like just so you have the idea of what we're going to be going into. So we get into a quick introduction into FPGAs, which David's going to handle. We talk specifically in some detail about an FPGA made by Xilinx, which is one of the two major companies that make FPGAs, the other being Altera. It's the Vertex 4, which he uses every day, and which is also the made FPGA based on this machine, this green beast. Then we go into a tool called Cowpatty, which is really an FPGA project, and we have a special guest ninja who we're going to bring up on stage to talk more about that, as well as Airbase, which is another guest ninja special. And then finally, I talk about cheap crack, and we'll sort of play off each other as we go along. It is the last talk of the day, on the last day of the conference, so we're going to, woo, woohoo, woo! I wish it was a beer, but it's a Pepsi, but it's free, so I'm not complaining. So we're gonna go into the details of Cowpatty, the details of Airbase. I'm gonna talk about cheap crack, and to be fair, cheap crack is, unlike this well-produced piece of sexy hardware, cheap crack is essentially something that we're releasing actually at TourCon at the end of September, early October. This is a sneak peek for people who are interested in FPGA stuff, which is hopefully is all y'all in the room. So we're not releasing cheap crack. I'm just going to talk about it. And one of the self-serving reasons I talk about it is because it is essentially a community project, which we'd love to get other hands on and other funding for. So if people have like 10, 20 bucks to throw towards it, or want to just pimp it on a website, or just give us ideas, certainly David and probably most of y'all in the room know more about FPGAs than I do, yet I'm doing the project. So with that, let's move into it. I'll let you do this.
Oh, okay.
I'm going to drink.
So FPGAs, just as a quick intro, how many people in the audience have heard of an FPGA? And
Word.
Wow, okay. How many have actually done some cool hacking stuff on FPGAs? Okay.
How many want to?
Awesome. Yeah, how many people want to, yeah? Woo! Yeah! So an FPGA, if you don't know what it is, but it seems like most of you do, so I'll kind of skim through this really quickly, is a collection of different types of gates, flip-flops, other components like block RAM, DSP-48s, DCMs, LUTs, all sorts of different components that you can just connect together however you want and make any sort of logic that you want. And this is actually a picture of a Vertex 4 LX25. I don't know if you can see it with the contrast on there.
Can everybody see it in the back? Is the text readable? Yeah? Okay, great.
So if you can see the blue highlighted areas, those are actually the input-output blocks where all the pins actually come into the FPGA die. And in the middle, that's where all the DCM sort of stuff, well, all of your clocks usually get routed through there, so they're right close to the DCMs and close to the middle of the FPGA, so it can route out to all of your logic. Then you have a ton of slices, which are in these rows. They're basically like the workhorse of the FPGA, where everything gets routed and done. And the LX25 has about 10,000 of those, just to give you an idea of how many different units are in there. And then there's a bunch of DCMs that let you multiply and divide clocks however you want. So if you have like a 50 megahertz clock coming in, you can multiply it up to like 300 or 500 or divide it down to whatever. And there's 8 of those on the LX25. And then there's some rows of RAM, block RAMs, which are kind of similar to like cache on your processor. With this, you get 72 of them. Each one of them is about 18 kilobits. So you get a fair amount of storage that you can just use for storing general purpose sort of stuff, whether you don't want to store in registers. And then on this particular model, there's DSP-48s in this one row along here. There's 48 of those, and you can do really high-speed multiplies. Basically, each of them you can do like up to 18 by 18 multiplies at 500 megahertz, basically. So, and you can do 48 of those in parallel. So it's actually quite a bit of power for if you're doing multiplication, and you can also chain them and do addition, things like that. Then there's this programmable routing matrix where I believe on the LX25 there's about 18 layers of just routing. And so everything is essentially kind of connected to everything else, at least somewhat directly. And so you can have something way over on one side of the FPGA that's talking to something on way on the other side, and it's just automatically routed through this huge matrix. So now DNM's going to do an intro on the WPA stuff.
So WPA, part of the project, one of the projects that David and a bunch of other super ninjas are working on is the ability to use FPGA hardware. And again, by saying FPGA hardware, I'm being slightly redundant. What I really mean here is reprogrammable hardware to accelerate the cracking of WPA keys, right? Encrypted WPA keys. And so WPA, who's familiar with WPA? Who's heard of or used WPA suite? Right, so essentially successor to WEP, right, for 802.11 networks security, right? Better network security characteristics generally than WEP, although it's hard to be worse than WEP. But having said that, no, I mean, basically, the protocol is not as breakable as easily by far. So the idea here was to build a model of WPA and then find a way, like, what are the easy ways to build essentially dedicated hardware for cheap? Comparative to, and all these things you gotta remember are comparative to the cost of fabricating your own ASIC, right? Your own actual chip. Because FPGAs are reprogrammable. I should mention, we should show the card. So a Vertex 4, which David just went into, is about yay large. Like this is a board, the Vertex 4 is this, right? Pull up. So this is the whole board, and this is the Vertex 4, the silver die looking thing, right? That's the Vertex 4, it's essentially one Vertex 4.
Yeah.
All right, on one PC card, right? Like this is essentially like a PC card form factor. And they also come in.
Yeah, the demo we're doing is actually on our compact flash cards, and so the FPGA on this is actually like much tinier. It's really tiny, and that's the LX25. And this is actually, you can get this with like over twice the amount of logic as the one for this, so this one's actually pretty decent. Yeah, right, all the demo for this is going to be done on these little cards.
Basically a huge parallel machine full of compact flash cards. But anyway, so getting back to the idea behind WPA here, the whole idea is how can we actually make, essentially a hardware-accelerated WPA cracker, right? Now this is not a project that I worked directly on. I was sort of aware of it, and I knew people who were working on it, knew David, knew some of the other super ninjas who were involved. But this is an example of WPA. So if you're familiar with WPA, this is essentially a little review of it. But basically, the first process here is to go get the key from the authentication server, right? You get the pairwise master key, PMK. Then you do the PTK transaction, TTK. I'm blowing through all of this because really this talk is not an explication of how WPA works or doesn't work. This is a model, and the idea here is just to point out, well, what can you actually attack, right? Like, what is the threat, the attack surface, or the threat model for WPA? I'll let you do this one.
Oh, okay.
We'll switch off.
Okay. So yeah, basically you type in your passphrase into your access point or into your wireless client, and it actually runs it through this pbkdf2 function that hashes it with SHA-1 a bunch of times, and then it takes that value and uses that for the actual, like generating your PTKs, your pairwise transient keys and stuff like that for the actual network authentication and for using like for all your encryption and stuff. So, come on. Yeah. So if you look at the pbkdf2 function, it actually runs pbkdf2 twice. And if you look at the code here, it's basically running SHA-1 HMAC 4,000 times, and then it does that again. And so it does tons of computing, like just to create this hash. And they run it 4,000 times just so it takes forever. So if you're trying to generate these things and you're a malicious person, you can only, it's way slow doing it. So if you kind of dive a little bit further and look at the SHA-1 HMAC function, basically what it does is you take your passphrase that you type into the access point, and it gets XORed with some values, and it gets run in SHA-1, if you know what an HMAC does. And essentially, like with this inner loop here, I don't know if you can see the mouse there, the inner loop, that will end up having like the same inner state every single time you run it, because the master key never changes. And so there's like this inner kind of state, and then that gets kind of fed into the next one. It basically gets appended on when you run this outer SHA-1. And so the cool thing is that you can just cache like the immediate one here, and so it cuts down on half the amount of SHA-1s you have to do. If that makes sense. Does that make sense? Yeah? Oh yeah, salt, yeah. So Is there salt in here?
Oh, thank you.
Oh, cool.
Do I have mic range to get off the stage? Nobody know? Huh? Probably? All right.
Yeah, so
can you hear me?
So that's one of the optimizations that people use to try and crack this, and so that's one thing that I take into account here. Yeah, the other thing that he brought up is that there's also a salt involved. It basically takes SSID and runs it through this before this whole chaining process. So there we go. If you see here, the first SHA-1 HMAC is actually done with the master key and the SSID at the access point, and then it gets run through with where basically the state keeps on getting appended on with the master key, like running the SHA-1 HMAC. And so all this is dependent on the SSID. The SSID is basically the salt for the whole process. And once you can generate the PMK value, then you can essentially run it through, figure out what the network traffic should be kind of like different values in the network for the exchange, and then you just compare it to a capture that you grab of the authentication, and then you can see if basically that's the right PMK for the transaction or not. So that's essentially how the cracking stuff works. Josh Wright up here actually wrote cow patty. I think he's down in the corner maybe. Yeah? Yeah.
Stand up.
Yeah, stand up. Woo!
Stand up. Oh, come on.
So, yeah, he wrote cow patty and...
One of our super ninjas.
Yeah, super ninja. And so I just took cow patty and added in hooks for cracking it with FPGAs. So on each one of these cards in here, I'm only doing the demo with 8 cards, but this system takes like 15, and it's kind of stupid because these things are so small that, and that thing's so big. So we have to build a better backplane for it, but each one of these cards has 8 SHA-1 cores in it, and we use block RAM to basically buffer all of the words that are fed to it. So the different passphrases that we use for it, we just send it out to the block RAM, and as long as we're able to keep the buffer filled, then it keeps the pipeline all nice and clean. And so all the SHA-1 cores are utilized fully as long as there's enough bandwidth there. And it's really slow, so it's really easy to keep the buffer filled. And this is basically how it works. It's essentially a ring buffer that we're using. And so the computer goes along and it starts filling in these different slots with basically just passphrases. Well, kind of the state after when we start going into the PBKDF2 part. And so it goes along and it starts filling these things up, and once it gets to the bottom, then it fires it off and says, okay, go FPGA. The FPGA starts grabbing the stuff, yeah, starts grabbing these values out and feeding them to the SHA-1 cores. And then it'll go on to the next 8 and feed them off when those are done. And then the computer will continue to fill the buffer right behind it. So as long as you're able to fill it within 256 of wherever its pointer is, then it keeps it nice and full, and you get like full utilization of all the cores. So that's one of the little things that we do to make sure that you get maximum performance out of it. So then yeah, it goes along, and then once it reaches there, then it kind of waits until that block's done processing, and then it goes on and keeps on filling it. So some performance comparisons here. With cow patty on a PC, like on a cheap Ghetto P3, you get about maybe 25 per second.
Why are you insulting my main workstation?
Okay, on Josh's workstation, if you hack his workstation and you want to include it on your cluster node, then yeah, you're only getting 25, so it's probably not worth it. On a 3.6 gigahertz like P4, you can get about 60 per second. On AMD Opteron, about 70. On Beetle's laptop over here, if you want to own his laptop, you can get about 70 per second on like an Intel Core Duo. And that's actually like, that's actually 35 per core or something like that, right? So with one of our little compact flash cards here, we can get about 430 per second.
We beat all of you.
And in this sort of cluster, we get about 65,000. On one of these cards, we can get about 1,000 per second. So in a cluster like this, if you fill them up with these, you get about 15,000 per second. So yeah, basically almost like 100 times, well, about 60 to 70 times faster than Josh's laptop over there. So pretty exciting. Supposedly AirCrack has some like MMX optimizations, and you can get about 100 per second on like a top-of-the-line P4. but we haven't really looked into that too much. Just wanted to throw that up there.
And so notably, the whole point of like those performance numbers is just to show the idea that yes, actually using programmable hardware to accelerate the process that we're trying to do does work, right? It's a feasible solution to what we're trying to make happen.
Yeah. So results. I threw all this stuff together, and RenderMan contacted me, and he decided that he wanted to compute hash tables for top 1,000,000 passphrases for the top 1,000 SSIDs. And so I had, this box laying around, and nobody really was buying it, and so I was just like, hey, I'll give you a shell on it and just crack away. And so one thing that's kind of funny is RenderMan sent me this email saying like where he got all these passphrases from, and I guess 43,000 or 430,000 of them are from like Mark Burnett and Kevin Mitnick, and they're actually harvested passwords from some systems they hacked supposedly or something, and they padded out to 1,000,000 passphrases with like a bunch of other stuff, and stripped out all the short ones because the passphrase has to be between like 8 and 64 characters. So RenderMan took all this stuff and he tried computing it on his like lab of workstations. I don't know, he said his cluster, so I assumed it was multiple machines. And it took him about a month to compute all the stuff on his cluster. And then he found out that every word in his word list had return characters at the end of each word, and they weren't filtering it out in CowPatty for some reason. So, yeah, after computing for a month, after computing everything, he found this out. So he sent me an email, asked me for some help. Help me! And this system here did it in 2 days. So pretty quick, about 48 hours it took. So I'm going to do a quick demo. This kind of sucks because I can't see the screens over here, so I'm just going to start it up.
Stand in front.
Oh, you're going to stand there?
Yeah, I'm
okay.
going to stand in front.
So demo time. Yeah, but I'll start this up just so.
Can people hear me on the mic still? Yes? Cool.
Yeah.
I'm going to, in order not to favor one side too much, I'm going to try and ambulate.
Yeah, this will be a little difficult, but.
You want me to hook it up in the back?
What's that?
Can I hook it up in the back?
No, I can hook it up. I'm just trying to get things set. Okay. Wait, let me start this up first, just so it's actually there.
It's beeping.
Okay, it's starting, so you can switch it over. So I took CowPatty, and because we're basically running one CowPatty instance for every card in the machine, I just set up a little script that creates a screen session and like creates screen sessions for every single instance of CowPatty, and automatically splits up the dictionary and just runs it. Can you see it over there?
Yes.
Okay. So
you've gotten the PSK Family Movie Night.
I just found it.
Yes.
Oh, okay. All right. Yeah. Well, that was going through like the 1,000,000-word thing, and it takes only like about 10 minutes or something to go through the whole thing, 1,000,000 words or something like that. So yeah, it's kind of I can't really see it from here. So so essentially, the PSK for this, I mean, these are all the ones that's tried. These are the different key numbers. The PSK is Family Movie Night, 4,769 passphrases tested in 10.7 seconds, 445.78 passphrases per second. Yeah, and that's just one instance. There's also 7 others going on.
Right.
So, yeah. Another screen session.
Switch.
They automatically die whenever one of them finds it.
You're on 3 right now.
I'm on 3?
Yeah.
Oh, okay, cool. Yeah, I think all of the other ones are dead because they didn't find anything.
Okay, yeah.
So, yeah. I don't know.
Is that it?
Let me try. Does that work?
Yeah.
Yeah. Okay. So you can see it going.
Starting up CowPatty instances, and now it's going through keys. 23, 25, 2600. So
I think that's like towards the end of the word list, but it should.
It's in
find
ours
it
in
another
essence.
instance.
Yeah. Yeah. Family Movie Night again.
Oh, okay. Yeah. So that's the demo. It does it really fast, and
yeah. Basically, it's not impressive, which means how fast it is.
But yeah, if I ran this on the actual machine here, we'd be waiting here for the whole lecture, trying to, wait for it to complete. So.
All right, you have your screen back?
Yeah. All right. And you can also use GenPMK. I don't know if you've heard of that, but that generates basically a dictionary kind of like file that you can later use for all your cracking stuff. So it's kind of like a rainbow table for WPA, and That's what we use to generate all these pre-computed hash tables and stuff. So you can use this to do that. As long as you have the SSID and a huge word list, you can just have it run and crunch on things. Ah, yes. So Beetle down here in the front actually found this little tidbit over at layer 1, and he was pretty excited about it. It's pretty sweet. What's that?
You're probably seeing that one easier.
Oh, okay. Yeah, so he found out that there's actually this airport utility in OS X that lets you feed it a PSK and an SSID, and it'll actually generate a PMK. So basically the whole PBKDF2 function. And so he just whipped together a little Perl script, and we could totally make fun of him on this because he just found some bugs in it.
And we should.
And we should, yeah. I mean, like, look at this. He's like assigning this variable like in the middle of the for each loop here.
Let me get down with the laser pointer. Hold on. Let me point it out.
Well, no, wait. Actually, that's not too bad. But
No. I mean, no. It's... no.
But he's not using my, and my God, what an animal.
Yeah. clearly, not. Yeah. But like Perl, it does work. So.
Yeah. So he's getting about 20 passphrases per second just with a ghetto Perl script that he threw together in OS X. And so yeah, this is ghetto PMK, basically the ghetto version of cow patty. And
right, single-threaded.
Yeah, single. So yeah, that's all of the WPA stuff. I guess if you have any questions, you can save it till the end. Johnny's going to come up here. I don't know if you know Johnny Cash, if you saw his wireless thing.
If you don't know him yet, you will know him now.
Yeah. So he wrote Airbase, and I modified his stuff to run with FPGAs, and so he's going to give us a small rundown on
Guess Ninja.
what Airbase is about.
Thank you very much.
Yeah.
Here, I'm going to give you my microphone.
Oh, okay.
Oh, I hate these.
Pardon me for the microphone switch here. She's singing dance.
Yeah, that's all right. I don't like clicking into anything anyway. Oh, okay. I feel important. I've got a mic. I feel like I'm on the news and stuff.
Speak normally.
Okay, so can everyone hear me? No feedback? Sounds good to me. All right, so I'm the one that created Airbase, which is pretty much just a suite of 802.11 tools. And I had written a lot of 802.11 stuff before, and they were all their own little program. And finally, I said, to hell with it, and put a big library around them all and started rewriting them all. And a few months later, I had what I called Airbase. So I started out with JC WebCrack, which is a distributed web cracker. JC AirCrack, which was just a C++ reimplementation of AirCrack, and anybody who's read AirCrack knows it needs a reimplementation, but aside from that, God, it's ugly. And then there's a whole bunch of tools. I'm probably going to spend too much time talking about the rest of the Airbase, just the hardware accelerated a bit, which at this point is just JC WebCrack, though in the future, JC AirCrack, hopefully the near future, JC AirCrack will be hardware accelerated as well. That'd be cool, huh? So, yeah, I got a lot of tools, using them with wireless cards. That's what I was doing before for my other talk. It was fun. JC AirCrack. JC AirCrack pretty much comes with a re-implementation of everything you've come to expect in AirCrack, arrow dump, PCAP2 IVs, merge IVs, everything. It also comes with some really elite ANSI animation, which I can't show you on the PowerPoint, but it looks really cool when you see that key found thing pop up.
We're going to show it later.
Oh, we are?
Yeah.
Oh, bitchin'. I guess you'll get to see it,
Well,
huh?
not the AirCrack stuff, but the...
Okay, yeah, I guess you still get to see the animation. Cool. So you'll see the animation. It started out in AirCrack. Anyway, the stuff at the bottom is actually kind of useful. It shows you which of the 17 statistical attacks, or 16, I guess I didn't do the last one, has actually landed you some points when you're trying to crack the key. So attack number 0 here, which is the original, got us a lot, and attack number 1 got us some. I think that was Hikari's, and then there's some more. 15 got you some, the rest didn't really do much. Okay, so JC WebCrack. JC WebCrack is actually the hardware accelerated portion of Airbase at this point. Comes with 3 different executables. There's JC WebCrack D, the WebCrack client, and the Pico client. So this is a picture of JC WebCrack D. This is the daemon that sits listening on your server waiting for clients to connect, and it's just going to check out a chunk of the key space to, whoever connects. So it's kind of like SETI at home for cracking web keys, right? And a lot of questions I get asked is, why would you ever try to just brute force a web key when you can run a statistical attack? So how many people here have successfully run AirCrack? Could I see? Like crack somebody else's network? Yeah, like 8. Okay. It's a pain in the ass. Everybody talks about, oh, statistical attacks are so bad, they're so bad, crack any network, doesn't matter if key size. And that's the key. The statistical attacks work on 128-bit keys, and you can't brute force a 128-bit key. But on a 40-bit key, I wrote this program and I ran it on my cluster I built for a school. Yeah, I guess I shouldn't get into that too much. They cut me off a while ago, which is why I started messing with FPGAs, because I couldn't get to it. Anyway, so the cluster had, I don't know, 13 Athlon 2200s. So that's pretty modest, I guess, in terms of clusters, but it's cool to have for myself. And they could crack a 40-bit web key in like 24 hours. It was actually pretty cool, because it was really like right up to 24 hours was the worst case scenario. So one day turnaround, no hassle. Like you start up the program, you want to crack your neighbor's network or something, you check the next day, and either you got it and it's a 40-bit key, or you haven't and it's a 104-bit key. And so there's two advantages of this. One, you don't have to sit around collecting packets and scratching your head. Why did it exit? Do I need more IVs? Do I need more data? Should I de-auth someone? What the hell is this program? Is it re-injecting ARP packets, or is it doing nothing at all? You know, it's frustrating cracking stuff statistically. It's a pain in the ass. So if you have a 40-bit network, this is, in my opinion, a lot less of a struggle. And the other advantage is there's no way to know if your neighbor's network is a 40-bit or a 104-bit one unless you brute force the entire 40-bit key space, and it doesn't work. At that point, you know you've got a 104-bit network, and you can bust out the cranky statistical attacks and sniff packets for a week and get lucky. So currently, this is how it's set up. You have JC WebCrack server, the WebCrack client. Oh, and then you have a bunch of WebCrack clients, sorry, and they're all just checking out chunks of the key space, city at home style. But once you throw in an FPGA, you could have a bunch of client, computers. Maybe you've taken over your school's computer science lab. Maybe you've got a cluster. But however you get them to do it, you can have a bunch of normal computers connect and check out the key space, as well as having, if you've got an FPGA loaded into a laptop, you can have it check out key spaces as well. And the server doesn't care, it just sees one guy doing a lot faster. No big deal. So the current architecture is this, and I'm going to show you the future architecture in a minute. So right now, JC WebCrackD has two different programs talk to it, the Pico client and the WebCrack client. And they talk the same protocol, but it means that the Pico client has to talk to the hardware, and the WebCrack client doesn't know about it. And it would be more elegant if you just had one program that knew how to do everything. And also right now is JC AirCrack, you see, is talking to Airware, and so is the WebCrack client. And Airware is my library that does all things wireless. And so it's using the library to crack the web key. It's got functions in there to try this key, brute force this, or whatever. So what I'd like to do is, instead of just having the Airware library know how to brute force keys in software, just abstract everything away into the library so that, if you've got an FPGA hooked up, great. Everything that I've ever written will now run hardware accelerated, including JC AirCrack. If you don't have an FPGA, that's cool. I'll do it in software. And if you've got some other hardware that could do this later, like a GPU, you can reprogram those if you know what you're doing. Maybe it could target that later. And if anybody's ever seen OSX's core image stuff, this is kind of inspired by that, because that's a really cool design. It sort of has the same look to it. So basically, how the Pico client works is gets a start key, a stop key, a key size, and a hopeful PRGA, which is a pseudo-random generator output, I think. Anyway, it sends it off to the FPGA, and then it says, okay, FPGA, go. Seems that's how these all work. You send the FPGA some stuff, and you tell it, go, because it's just dying to do something. So, and then the client, all it does is, while the Pico chip is busy, update the display. It's not using any CPU cycles there. It's like, you done? I got nothing to do. So what you could do with those CPU cycles is run another copy of the, software-based client and get, more bang for your buck out of your CPU. So that's all of Airbase. That's a lot of code. In fact, I checked yesterday, and I have 20,000 lines of wireless code. They all compiled on x86 OSX without changing anything except one line. So that was cool. Anyway, here's this is back to Dave's stuff.
Thanks.
No problem.
Thanks a lot, Johnny.
Whatever.
So I'm going to talk a little bit about the specifics on how the FPGA core works that we use to accelerate all the RC4 stuff. Right now, you can either use an image that I made that has 32 RC4 cores or 48. And all these, I made all of them so they're really lightweight, really tiny, so you can just fit a ton of them on the FPGA. And yeah, I'll go into the performance numbers later, but it basically wraps around a block RAM on the FPGA. So the block RAM is used as an S box, and there's just a really tiny state machine that just handles all of the sort of RC4 stuff around it. And it'll just try every key with, from the start to the end and spit out PRGA and just compare it, and it's a pretty simple brute force algorithm. So if you look at RC4 normally, it's a really simple algorithm. Basically, you just have your initialization where you create this permutation between like 0 and 255. So it's just assigning like each index into the S array to whatever the index is. And then it kind of goes through, and based on the key, it just starts mix and matching, like swapping different values inside the S box. And then eventually, it kind of does some more swap stuff and outputs a byte during every cycle in the PRGA step. And then that's your basically random output based on your key. So if you put in a key, you'll always get this random stream of bytes that can continue on until infinity. But yeah, basically that's how RC4 works. It's just basically a PRGA algorithm. So right now, the computer just sends a start and a stop and whatever the expected PRGA is. And you get the PRGA by basically grabbing a packet, and you know what the first like 5 to 8 bytes or whatever the packet is. So you XOR that with that, and then that should be the bytes that come straight out of RC4, if that makes sense, because those get XORed onto the data, the actual payload for the packet. And so with that PRGA, you're just looking for a key that will match up with the PRGA that you're getting. And so right now, the computer feeds this over to the RC4 keygen thing over here, and then it starts farming out keys. It says, okay, RC4 core over there, try key 0, and then you over here try key 1, and you over here try key 2. And then it sends back a PRGA, so one of them says like, hey, yeah, it's actually woot, it's actually going to be some hex values or something, but just for fun. It actually
spend a lot of time on this, because this is our good slide technique right here.
What's that?
This is our good slide technique right here.
Exactly, yeah. It's all metaphorical to some cool hex values. So then this one says arg, this one says Hammy's my hero, and then none of them match the bling over here. So
no
you
bling.
keep on going, farm out. Okay, you try key 3, key 4, key 5, and then they go back, and then it's like, oh wait, there's bling right there. So I guess that the key must be 4 because the PRGA is bling. So then it goes like, okay, the key is actually 4, and then it's all cracked. Some cool optimizations that you can do with RC4 and hardware is this whole initialization step. Normally you deal with the block RAM where basically you have an address, data, and then like a write enable or something like that. And basically every cycle you feed in, okay, address 0, write 0, and yeah, there's the write enable enabled, so just write a 0 into there, and then write a 1, and then a 2. And that takes 256 cycles to go through all of that. So the rest of the algorithm here takes maybe 500 cycles normally. And so adding on another 256 just takes forever. One of the first optimizations I thought of for initializing kind of in parallel while the thing's going on is to basically have 2 block RAMs where you kind of have your master block RAM over here, and then you have 2 of them, and in the first stage it just fills like block RAM A, and then this RC4 core over here starts using the A block RAM, and then it starts swapping values around and writing to it and stuff. And while it's doing that, then it's initializing B, and then when it goes on to cracking the next key, then it switches over to B, which is already all initialized and good, and so then it messes with that one while A is getting filled. So it just swaps back and forth. And so I thought that was a pretty good design at first, but it turns out there's actually a better way to do it. This better way is basically you're addressing it as an 8-bit block RAM, but what if you make it a 16-bit? And so for example, like if you read from address 2, you only look at the bottom 8 bits. If you read from address 54 or 57 or whatever, you only look at the bottom 8 bits. And in the KSA, you're writing to every single value in there because you're going through and swapping, like, okay, 0 gets swapped with this, 1 gets swapped with this, 2 gets swapped with this. And so you're actually writing to every single value in the whole thing. And so why not, when you're writing, just set like the top 8 bits of the 16 bits to whatever your address is. And so essentially like the top 8 bits in the whole block RAM will be initialized once you're done just by the pure property of the KSA because it writes to everything. And so, so yeah, you'll end up with like at address 0, there's 0073, address 1, 019B. And then once you're done with this whole, for your first one, you just swap over, and now you're using the top half of the 8 bits instead of the bottom half. And so it's kind of cool. With this, you only have to use 1 block RAM instead of 2. And it's a lot more fast because all your logic can be just right around the block RAM and stay really close to it. So that's one of my optimizations. If you can think of a cooler, better one, just let me know. So yeah, so then everything's happy here. I'm going to go on to a demo. Well, actually, maybe we should have a slight intermission and throw on a movie.
Yeah,
Yeah?
it's the last talk of the day.
Yeah. Might as well.
We should explain this particular slide though before we cut into this. So, well, you're good at this, so I'll let you.
Oh, okay.
You want to do the blank plus blank equals blank?
Oh, yeah. So this is a JC WebCrack D over here, and this is one of our Pico cards. That's a quarter right there, so it's pretty small.
This is essentially this card.
Yeah, and this is Neo like shooting up some shit in the Matrix. And you may ask yourself, what do all these things have in common? And you'll find out soon enough. But before that, we just want to take a quick break and.
So we're talking about the Matrix. We're also going to be talking about performance, and with that in mind, yeah, we have to mic it. We're get a little above this. We're gonna try and mic this ourselves. So hold on a second. Move a little up here. Okay. Can you hear it?
What did you think about that fighting and stuff in the Matrix? Do you think that it was, they like ripped those techniques off of you, or what?
You have got to be kidding me. That fighting couldn't be any further away from ninja fighting if it were a brick trying to beat Jupiter. First of all, the people, the actors are already fighting at a ridiculously slow level. If you took the regular footage of them fighting regular speed and then played that at 400 times faster, that would be about half ninja speed. Look, just get ninjas in there who can actually do it that fast. Unfortunately, it's difficult to capture us on film, which is at about 24 frames per second, and the human eye processes at about 72 frames per second, and ninjas can move at roughly 84,000 frames per second. On a bad day, it might get down to around 60,000 frames per second. We're really flipping fast, and we fight that fast. So, like, us watching The Matrix is like watching a retarded bear in the circus. It's painful and it's annoying, but it's just frustrating because you wish there was something you could do, but you don't really want to watch it. Nobody really wants to see that. They're on a little bike, and you're just like, take them away from all of this. I put in an order form to try and kill everybody associated with the Matrix. Hopefully that'll come down the pipe someday soon, because I would like to give those Wachowski brothers a couple fists in the head. V for vendetta. Well, I've got a vendetta against the Wachowski brothers.
So that's our interlude. Okay.
So the metaphor out of that whole video is that like your server cluster is those dudes in the Matrix, and this is kind of the ninja stuff here. So.
All right. You want to get set up and tell me when you're ready?
All right. So on these cards, we've got different images loaded onto this little flash chip that we have on there, and we can swap them out on the fly. So before I was running the image for Cow Patty, and I just swapped it over to use the stuff for the Pico WebCrack stuff, and you can have like up to about like, I don't know, 60 different images on there, and you can swap them out, and it takes like, maybe about 1 or 2 milliseconds to swap images. So that's the cool thing about reconfigurable computing. Let me start up the demo here.
The other cool thing about reconfigurable computing is reconfiguring the monitors.
So I made another screen script that basically fires up the JC WebCrack daemon, and then fires up, why don't you switch it over?
Here, I got it.
Okay.
Give me the other one.
Oh, yeah. This should take a little while to crack, so.
All right, magic hour. Yay! All right, so come on down, come on down.
Oh,
we can describe it from here.
Oh, okay. All right. So yeah, this is running the JC WebCrack client. This is actually one out of 16 instances that are running right now. And this particular instance is doing about 3 million keys per second, and so that times 16 is pretty fast. And it should go along and eventually find the key. I think this is the session that'll actually find it, and Johnny added in a cool animation once it finds it, so we'll wait for that. Let's see. Yeah, so each card gets around 6 million keys per second, and in the 48 core version, then you can get about like 9 million keys per second. On
almost 10
computer,
million.
What's that?
Almost 10 million.
Almost 10 million, yeah.
Basically 10 million.
Yeah, so on my laptop, my huge frickin' like P4 3.6 gigahertz laptop, I get around maybe 1/3 of a million, like about 300,000. So it's pretty quick. It should be coming up soon here, I think.
Yeah, bear with us in our supercomputing.
There we go.
Hooray!
There we go. So that's the demo of that, yeah. Yeah, ask Johnny later about how he did the matrix effects. So yeah, those are all the performance numbers here. But yeah, we can brute force, one of these systems can brute force a 40-bit key in around like, I think 13 minutes or something like that, or pretty quick. There you go.
Yeah, sure. All right. So, WebCrack plus FPGAs plus matrix-like effects and processing power, times Ninja equals performance comparisons, because we're obsessed with numbers. So inside, JC WebCrack, what are we getting, right? On a PC, 1.25 gigahertz, 150,000 keys a second, right? 1.25 gigahertz G4, right, basically. And a P4, 3.6 gigahertz P4, about twice that, 300,000 keys a second, right? On an FPGA, as we just said, basically Pico WebCrack on an LX25, which again is these compact flash, this particular compact flash kind of chip, running, what, 15 of these?
Well, that's for one of them, and that's 15.
This is for one, right? So for a single LX25 is 9 million per second. For a cluster of 15 a la the Green Beast, 135 million keys per second, right? 135 million keys per second. So in 60 seconds, 135 million times 60 is really a lot, right? So in a minute, you could do essentially over a 500 million, right? Essentially. And then an FX60, is this an FX60?
Yeah.
So in one FX60, as opposed to an LX25. So LX25, FX60, right? 18 million. So twice this, essentially, right? Per second. So.
Oh, yeah.
All right. So now we'll totally switch gears and get off the whole matrix thing, only because I don't have any more cool videos. If we have time, actually, I have other things I can show. But who here remembers a thing called deep crack? Excellent. All right. So deep crack, for people who don't know or aren't sure, the slide sort of allocates things. I'm just going to go down this. Deep crack was a project that was initially sort of dreamt up and commissioned by John Gilmore and the EFF, the Electronic Frontier Foundation. And as a disclosure, as an item of disclosure, I have to announce that I worked for the EFF a couple years ago as a staff technologist. I'm no longer there, but they're all very good friends of mine. In 1998, for a number of reasons, one being that the US government was still saying DES was secure for certain kinds of classified information, not classified information, but for certain types of classifications of information, DES was still an approachable option. And vendors also were saying the same thing. Vendors were happy to sell you DES in forms that you could use and call it secure. And so, of course, there were all these different DES challenges. There was DES-Chow, which was the first one, I believe, in '97, which was broke by Matt Curtin and his team. There was also an RSA challenge, or a number of RSA challenges. Most people remember these because of distributed.net. Who remembers distributed.net? Who still runs like an RC4 client or whatever it is? Oh, anybody? A couple people? Holdouts. Holdouts. I mean, you know, just get one of these, right? And call it done, right? Go on with your day. Make a better cup of coffee, right? Do something else. RC4 is dead. So in an attempt to try to kick everybody into action, same as, you know, the rest of the talks here have been talking about exploits and vulnerabilities, and the same deal is the ability to actually throw money at hardware and make it just happen, right? So John Gilmore, the EFF, put together a project to build essentially a affordable, quote unquote, desk cracking machine, right? So when we say affordable, what do we mean? Now keep in mind, this is 1998. It's 2006 now, it's 1998, so it's about 8 years, right? We're just shy of a 10-year mark, okay? In 1998 dollars, notably more valued than now, they budgeted for around $250,000 and they spent about $210,000. I have varying numbers. One another number says they spent about $180,000 and they budgeted for $210,000. But regardless, right, we're talking around $200,000, right? $200,000 got you a machine, essentially, at the end of the day, that would crack the 56-bit desk challenge that RSA put out in essentially 4 days, average time, right? So what does $1998 mean today? Well, I did a little math, and so $210,000 runs up to about $243,000 and change. And $250,000 is the total budget. If we were as lucky as they were to not go over budget and actually go under budget, it's about $289,000. So let's just round up because I'm gonna have to go to conferences, I'm gonna have to buy people beers, etc. Call it 300 grand, right? $300,000 to do this, right? But since it's been 8 years, you get more for your money, right? Moore's law is in effect, if ever it was, and so you're not going to get the same exact hardware, even with the same ASIC design, even with the same VHDL or Verilog that you would write for the core. You're not going to get as bad performance because obviously FPGAs have evolved, ASIC manufacturing, fabrication has evolved, processes are smaller, right? We're talking about 0.13 to 0.09 process is approachable. So what did they build? Well, they built this. They built a machine, essentially, they used ASICs. We're using FPGAs, we're using reprogrammable hardware, right? They built ASICs, meaning they came up with a design and they had somebody fabricate them chips, right? They sent it to a fab, it was etched on silicon and built into a die and put on a board, right? They built essentially one custom ASIC design and they just replicated it. So they have essentially 1,536 custom desk cracking chips. Each chip is identical, they are exactly the same. There's no difference between one chip or the other, right? But there are 1,500 and change of them in a machine, okay? And then they built it in essentially 2 chassis. Who remembers like VME as a backplane? Like VME bus, a couple people in the back. Okay, so they basically took 2 Sun 2s, right? With a huge VME backplane and just built boards that plug into VME. They didn't use any of the electrics. They rewired the electrics and everything else. They weren't using like the protocols, but they were using VME backplanes to build these huge, monstrous boards. Each board had 64 chips, right? So 64 of these custom ASICs. They had 12 boards per chassis, and they had 2 chassis, so 2 gigantic Sun 2 chassis, basically, right? That was deep crack, okay? Each chip, of which, again, they have over 1,500 of, has 24 what they call search units. And the search unit is essentially the logic implemented to search through the key space, right? Both chassis, with all sets of boards, all chips up and running, some of the chips notably were there for failure, right? There was some fault tolerance built into the system. If a chip burnt out or got a short, whatever else, there was some amount of coverage there. But both chassis running simultaneously at full throttle will essentially, on average, crack a 56-bit desk key in 4.5 days, right? In 1998, almost 10 years ago, right? And EFF did us the favor of documenting the whole thing in a book, right? They laid out all of the source code that they used. In this case, they laid out all the VHDL source code. VHDL is one of 2 popular hardware design languages. There's Verilog, there's VHDL, right? They happen to use VHDL. I happen to write VHDL. David happens to write Verilog. I say tomato, he says tomato, etc. But basically, they laid out all the code. They also laid out all of the board diagrams. So you could replicate everything you wanted with this book. And they also gave you source code, which they pulled from the PGP project back in the bad old days when sending PGP across the internet was a bad thing and people printed it out in books to scan in Europe. they included source code that you could scan yourself, verify the scan was correct, and then use it to verify the scan of every other page in the book which had the source code. And they called this book, appropriately enough, Cracking Desks, right? I have a copy of this book with me. I forgot to bring it down to the talk, and it was sort of going to be my physical prop for this piece. But this is essentially a screenshot of the book, right? This is the book. Who has this book, out of curiosity? Does anybody have it in the room? Sweet. Have you read it? Have you paged through it? I mean, even if you don't necessarily all understand it, you know? So, me being low rent, right? I mean, David on the high end of the FPGA hacking spectrum, and me being like, you know, random garage guy, I started saying to myself, well, you know, I have an interest in FPGAs generally, and I have an interest in crypto, so let's combine the two. But I can't afford to sort of build, fabricate, and manufacture and sell things like this monstrous green beast, which is a huge value, actually, here in the market. But what I can afford is like little tinkery stuff, right, that I can get, you know, over the web, basically, right? And so I started asking myself the question, well, what would happen if you just took advantage of like 8 years of Moore's Law in not necessarily CPUs, but in FPGAs? Now, it's kind of weird because FPGAs don't have a core, right? You create a core for them. There isn't, Moore's Law says that, you know, what is it, microprocessors, or no, it's actually like transistors, right? Yeah. Transistor count will double every 18 months, right? Now, so FPGAs essentially have a bunch of logic, which you could arguably call is essentially just complicated transistor layout, right? Now, it's reconfigurable, so you have a certain amount of stuff that you can play with, right? So I was curious to answer the question was, well, I don't have $200,000, even in 1998 dollars or in 2006 dollars, right? There's no way I can approach that, right? But what I do have is a couple $100 laying around every now and then to play with interesting projects. What I also have is an interest in learning how to do this stuff at a small scale so that it's approachable to more than just me and people who have lots of cash, right? That was really the idea behind the EFF project. I mean, $200,000 is a lot of money, but not to a government, which is what they were trying to prove, right? A government can easily build this thing for less than it cost them, because they had to hire contractors, they had to hire specialists. A government can just say, you, work on this, break this thing, you get paid nothing, right? And it gets done, right? Some people in the audience have personal experience with this particular way of working. So, you know, I want to use FPGAs, and I want to try and do as well as EFF did 8 years ago, basically, right? And I'm kind of using the fact that it's 8 years, and it might take me till 10 years to get there. So I'm kind of padding my time budget by having a lot less money. So we set out some random numbers, like some random just scattershot numbers as metrics. If I only use a total of $10,000, and I use cheaper hardware, I'm not going to be able to fabricate ASICs. I don't have the money, the budget, the time, anything to fabricate ASICs. I can't make custom silicon. What I can do is buy commercial, off-the-shelf FPGAs, okay? FPGAs are a lot slower than ASICs, lots slower. Faster than CPUs, which are general processors, but lots slower than ASICs. But obviously, FPGA design is getting better and better all the time. And people use FPGAs in the ASIC industry to simulate cores that they then go fabricate. Right? So the FPGAs are essentially like the scratch pad of the ASIC industry. Right? It's easy to implement stuff in FPGAs, and then once you've got it right, you can turn up the fab and spend $3 million in Germany in an Infineon lab building, you know, RAM or whatever. And then what I want to do is what I call shoestring parallelism. Right? Getting a bunch of boards with simple FPGAs that cost like $100 a pop, like in the board, not like, you know, individually. And then just linking them together and making the design such that it's easy to do, right? It's not quite as distributed as, say, a distributed.NET, but there's no reason you couldn't do that also. But what I want to do is build essentially a shoebox of little boards that can essentially try to crack desks in a reasonable amount of time with $10,000. So, does it work? We're not sure yet. As a point of reference, to point out where's my, yeah, there. Yeah, so David has gracefully displayed the board. I'm going to hold this up. This is the board I'm talking about. And this is the board that I'm currently using. And actually, when I say that, I mean this board literally is the board I'm currently using. This is a small board made by a company called Digilent. They're available on the web, digilentinc.com. They are one of a number of people who sell essentially boards, development boards, and hobbyist boards for people to play with. This is like, this board costs about $150 off the web. And so as a reference point, can most people see this? I mean, there's not a lot of people in the room, so people can probably see it. So this board, as opposed to this kind of design, which takes both skill and money, which I have neither of, This I buy for 150 bucks, and I get essentially, this is a Spartan 3 FPGA, this little bit right here. The laser pointer may be visible, but basically this little bit right here is the FPGA. The rest of it essentially is just a board with a bunch of I/O and a bunch of, it's very well labeled. So if people have ever looked at hardware and they try to figure out what it does and like hack it, this is very well labeled. It's meant to be hacked. It's a development board, it's a test board, it's an educational board. It's used in a lot of college courses. And it has a ton of I/O. And when I say I/O, I don't only mean these ports, which take little modules that you can buy off their website. We have some that just plug into these little ports and basically offer up a USB or an Ethernet port. It also has VGA and serial. It also has PS2. It has 8 switches, toggle switches, 4 momentary switches, and a few other things, right? It also has some RAM on the back to store images and the like, and it has some other platform flash for boot up code and whatnot. Right? So essentially, it's a board you can play with, right? It's really easy to play with. And notably, this is not to say that the other hardware here, like these, are not to be able to play with. You can play with these. And frankly, if you come from a software development background where you just really want to write code and have it compile and do something, the closest you get to that is something like this from David, right? This is more of your like bedroom hacker, HP garage kind of mentality. I'm trying to play like I'm sort of a retarded version of Wozniak. So, you know, the idea here is, can I spend $10,000, hopefully of mostly other people's money, and build essentially a cluster or multiple clusters that can communicate over some, you know, make sense protocol that will crack DES essentially as fast as EFF did in 1998 for $10,000. Because $10,000 is both A, approachable for a person who just happens to make more than I do, which is probably most of y'all in the room, and C, or B, it's also approachable for people who, you know, just want a project, right? Cracking a data encryption standard that stood for 30 years is now a hobbyist project. Right? That's the key thing. That's like the revelation that we're trying to build here. The design in Deep Crack was pretty simple. So one of the reasons we think we can do better is that we can just make the design better, right? The design that they used in Deep Crack didn't include very much parallelism. There wasn't a lot of pipelining. They didn't really parallelize things. It's very simple. They did it specifically because they wanted to have a very simple core that they could verify very easily, because they knew that once they had this written in silicon, once it was etched in metal, they couldn't change it. Right? We don't have that problem. We can change it. Right? We can just change the design, upload it to an FPGA, and try again. Right? We may also be able to do better. We may be able to figure out better optimizations or algorithms than they had. Right? It's not to say that we think we know more, just that we have the ability to mess with it, and we can make mistakes and recover them easier than they can. Again, FPGAs are still slower than custom ASICs, but today's FPGAs might rival 8-year-old ASIC designs in some cases. Right? You may be able to actually get faster performance out of FPGAs with some kinds of tasks than you would have gotten cost comparatively, like price per cost, on an ASIC, an actual custom ASIC design. And so where is this all net out right now? Well, come to TourCon. TourCon happens in the end of September, early October. David helps organize and runs TourCon. We're aiming to have, just went the battery. Oh, okay. All right, we back? All right.
There we go.
So, you know, come to TourCon. We'll have more to talk about then. This is a sneak peek. So this essentially is the board. Right now it's running just really a test pattern. There's not much interesting to see. I will have essentially what I plan to show is a linked up PC sending data to these boards, and then, you know, actually having counters about how much each board is processing. So, conclusions. I'm just gonna put all these up in the first place. All right. Get an FPGA and start cracking. I mean, either you buy it from David and you like rock with the mastery that is, you know, essentially seconds to crack, like, you know, WEP, or, you know, help me out on this project, or, you know, come up with something yourself, right? The thing that we're both trying to encourage is more people to use hardware to do interesting things, right? And that's what, I mean, that's really why we gave the talk here at BlackHat, was because we wanted to get to the BlackHat audience the idea that hardware is approachable, either, you know, at the corporate level for the sexy green beast, or at the hobbyist hacker level for 150 bucks, you know, the cost of essentially 2 lattes. Make use of your hardware to break crypto. Like, that's the other thing, right? Crypto is not an impenetrable fortress, and really, you don't really have to know all that much about crypto. It helps, don't get me wrong, but if you can harness processing power alone from this project and from previous projects we've done, really that's what is key, right? And that's what Distributed Net tried to show as well, and it did so successfully for a certain extent. Go ahead.
Yeah, and make sure you use cool ASCII matrix effects when you can, or have Johnny code them up for you. That's what I did. Choose bad passwords. That's always a good, security tip. So just, go ahead and do that. What's that? Choose password. What? Yeah. Password's a good one. And use DES. DES is ultra secure, so use it for everything that you do, please. Yeah. Exactly. Yeah, it's a standard, so you should use it. So yeah, this is the E12. It's basically a compact flash card with 64 megs of flash, 128 megabytes of RAM, gigabit Ethernet. You can also get it with a 450 megahertz PowerPC on this little tiny compact flash card. So you can run Linux on it, or just pop it in your PDA and like crack stuff really fast, or whatever. Or throw together your own box with a bunch of compact flash to PCI adapters and heat sinks. Yeah, and heat sinks. And this is our supercluster thingy, the green box. This one takes 15 of them. It's actually got 2 motherboards in it, so that's why I was only demoing 8, because I'd have to switch over to the other motherboard in here to like demo the other 7. And yeah, so it's all standard, sort of off-the-shelf stuff.
I note you have 2 DVD-RWs in there. Have you tried implementing, I don't know, DVD decryption in FPGAs?
No.
No?
That's a good project, though.
No.
So yeah, you can build one of these yourself. We were having some trouble with Linux, and so I rewrote our entire driver for OpenBSD now, and that'll probably be committed like later on this week or something. So yeah, there should be native support for all this stuff in OpenBSD if you're interested in that. And then we'll probably have to rewrite a lot of their PCI stuff to get it to work in Linux.
Digital S3 boards. This is the one I just showed up that's sitting here, ticking away nicely. Again, this has a Xilinx Spartan 3. This is a much cheaper and much simpler FPGA than the Vertex 4s. Essentially, notably, I specified the XC3S1000. That designator is actually the Spartan 3 that if you were going to get a Spartan 3, because they're cost effective, they're very affordable for like little hacks, get that one. There's also, I think, a 200 and a 400 as opposed to the 1000. You want to get the 1000 because what the 1000 gives you is what they call million gate equivalent. One of the things you'll find in the FPGA industry is that there's all these terms that they use about gate equivalence, and it's like megahertz in CPUs basically, right? Everybody wants to create FPGAs that have a large number of gates on them because gates are the basic like addressable logic element that you use to build things. Like it's like the Legos, right? The issue is that nobody counts gate equivalents the same way. So a million gate equivalent Xilinx FPGA is not the same necessarily as a million gate equivalent Altera FPGA, right? But it is effective. And basically this board costs around 150 bucks online. With the 1000, it's cheaper. It's 99 bucks if you want to buy it with the 200, which is like a 200,000 gate equivalent. But I highly recommend getting the 1000. You'll have more gates to play with. It won't go obsolete as fast. You can tinker with it more. In my off time, I'm not trying to crack DES. I use this board to build essentially Galaga in an FPGA because it has VGA and it has a PS2 port, so you can build little FPGA. Like I basically recreate retro video games in a little board. It has 2 megabytes of platform flash, so a lot less, 1 megabyte of SRAM. Lots of very simple I/O, which is great to twiddle with. I like to twiddle things. I like to have little switches that make blinky lights. So that's my beef. And go to digitalandinc.com. We got to give shout-outs to a whole bunch of super ninjas. Johnny Cash, who was up here earlier, did Airbase, JC Webcrack, and JC Aircrack. Many props to him. I'm sure that after his new fame and fortune, he will disassociate himself from all the FPGA stuff and go on to new heights of owning. Josh Wright did Cow Patty, also super ninja, coming up with the ability to do that and for us to be able to add FPGA specialization to that. RenderMan was the PMK hash table monkey. Really, with him, he sort of started the whole process of actually getting the thing going and then screwing up accidentally and then actually getting David involved. Beetle wrote Ghetto PMK, which is very appropriate. I mean, it is ghetto and it is PMK and it works and it's great and it does. Also, I will mention threw some money towards Cheap Crack to get it rolling, to get us boards. And finally, Cowboy M, also in the audience, gave us Cheap Crack funding as well to get some boards and get the project rolling. And also, all of these projects generously funded by viewers like you. That's it. These are our email addresses, websites. Visit all of them. Send donations. Questions?
Oh, I'd also like to note that all of the code that I demoed on here, you can download. It's all open source, and it's on opencyphers.org.
Yeah.
Right now, it only runs on our hardware, but it's pretty easy to port it to other hardware. So all the source is there. Just do whatever you like with it. Yeah, and check out Pico Computing if you want to buy some stuff that it runs on right now.
And hunred.org is the place to go to find out more information about cheap crack. Thanks.
And also, one last thing, if you come out to TourCon, we're also doing some hardware hacking workshops, where basically, I don't know if you know Bunny, the guy that hacked the Xbox and like stuff like that. He's doing a workshop where he's basically giving you like this new device that he actually built that's normally like $150 or something like that. And you basically take it apart, figure out how everything works, hack it together, download the ROM, do some bit twiddling, build your own kernel, whatever, re-upload it, and make some hardware hack in this course. And right now it's only $900 for a day, and it actually includes all the hardware, and you get like a soldering kit and all sorts of stuff like that. And it'll be increasing up to $1,600. Just go to tourcon.org if you're interested.
I have, and before everybody takes off, or take off if you like, I have a Vista build CD of the latest build of Vista for anybody who can identify the person shown in the screenshot up there. Zatoichi, who said it? Somebody said it.
She said it.
Wait. Shush you!
Oh yeah, so any questions or?
Yeah, come on up, or buy us beers. Thanks.
Cool. Thanks a lot.